Good afternoon, everybody. It's just turned 12, so I'll make a start on this fourth webinar in our Train Talks at 12 series on wheel rail friction management. Today, we're going to be looking in more detail about rail corrugation damage and how friction management can help to mitigate against it. For those of you who haven't joined one of these webinars before, I'm Jackie Butterfield and I'm the lead applications engineer for LB Foster in Europe. And as before, in our previous webinars, my colleague Zoe Loveday is here to assist, keep an eye on the chat and keep me on track time-wise and field any questions that you might have. If you haven't been able to catch any of our previous webinars, don't worry, they are all recorded on our website. And at some point, we'll pop them onto our LB Foster YouTube channel as well, so that they'll be all publicly available. So today's webinar, I will start, as always, with a quick recap of why it is always important to control friction in the wheel rail interface. And then we'll look at the mechanisms of corrugation damage formation. And then, obviously, as we are from LB Foster, we're going to look at the friction management solutions that are available and that can be employed to mitigate against corrugation, and also the consumables that you would use in the equipment. And then we'll finish up with a few case studies where friction management has been very successful in mitigating against corrugation, and then a reminder of the upcoming webinars in our series. So as a recap, in all of these webinars, we've started with this slide in terms of why do we need to control friction. So without friction in the wheel rail interface, there would be no movement, there would be no traction and no braking. So friction is required. However, uncontrolled friction is bad. And whether that is high friction levels or excessively low friction levels, this uncontrolled friction can lead to a number of issues, which some of the images that you can see there in terms of wear, rolling contact fatigue, corrugation, and also low adhesion. So all of these damage mechanisms are possible with low or excessively high friction. So it's very important that we control friction to avoid these. So what actually is corrugation damage? So corrugation damage is a regular repeating pattern of damage on the rails with a set wavelength. So there are a couple of images here on the right showing corrugation damage. So you can see very clearly that wave formation repeating pattern of damage on the rail head. It can occur in both curves and in tangent track, but it tends to be more prevalent in curves, and depending on the type of corrugation, predominantly on the low rail of particularly tight curves. So corrugation in itself is a damage, so we'd like to avoid it, obviously, on the railhead, but it in turn can lead to other issues, such as increased wheel rail vibrations, which then can lead to damage to track components. Excessive vibration obviously can lead to ballast and track bed damage as well, with the increased vibration. The corrugation in itself, because it's a wave, it will generate noise, which can be extremely annoying and damaging, particularly roaring rail, which is a phenomenon which can give you very, very high noise levels, above 120 decibels in some locations. It can also reduce ride comfort. So any extensive vibration will affect the suspension characteristics of the vehicle dynamics, and will also affect the comfort of the passengers of the vehicle. And all of these things, if corrugation is left unchecked, there is the potential to risk operational safety. There are several types of corrugation damage, each having characteristic properties, wavelengths, frequencies, and they each have a slightly different formation trigger that triggers the waveform damage. However, the underlying mechanism of the formation and propagation of corrugation is essentially the same. So here we've got another few pictures of corrugation damage with different wavelength patterns. So the center one is a very, very short wavelength damage pattern, and the two outer ones are slightly longer wavelength damage patterns. So the one on the right it is quite a long wavelength damage. So the mechanism of formation of damage for all types of corrugation can be explained by this diagram that I'll talk you through now. So this diagram was first proposed by Professor Stuart Grassi, and he's probably one of the, if not the leading expert on corrugation damage in the world. So we start off with the initial rail profile, and then something happens within that initial rail profile, some discontinuity. So it could be a rail joint or an abnormal weld or a defect, a squat perhaps, and that causes or triggers a wavelength fixing mechanism. So this wavelength fixing mechanism actually determines that wavelength and frequency of the corrugation damage. And this is related to the vehicle, the dynamic behavior of the vehicle track system. And the action of repeated traffic or vehicles with a similar dynamic behavior just reinforce that fixing mechanism. This wavelength fixing mechanism fixes not only the wavelength, but also the position of the eventual corrugation damage along the track. So other parameters also influence this wavelength fixing mechanism, particularly the way that the vehicle behaves, so the traction characteristics, obviously the track geometry as well. So creep and creep forces influence that. Also, friction is a large player in that, and also stick slip behavior, which we talked a little bit about last time in terms of when we were talking about squeal noise. So all of these influence that wavelength fixing mechanism, and if they influence them, if we can then influence them, we can help to mitigate the damage. So this results in a dynamic load or a dynamic force, and this in turn causes the damage mechanism, which in most cases is wear, but in some types of corrugation can also be plastic flow and can also lead to rolling contact fatigue damage as well. So this damage mechanism then causes a change to the initial longitudinal rail profile, and then it goes through this feedback loop with the wavelength fixing mechanism to form this repeating pattern of damage. And over time, the depth of the damage will increase because the passage of vehicles, they've all got similar dynamic properties. They will tend to reinforce that wave damage. So the depth of the damage will increase over time. So obviously this will cause other effects such as noise generation and damage to the track components. And obviously if it's left completely uncontrolled, potentially you could lead to a derailment and other operational and safety issues. So that's the mechanism. The corrugation frequency will indicate the underlying mechanism of formation and that wavelength fixing mechanism. So here's a table that comes from one of Stuart's papers, which just lists some of the identified characteristic forms of corrugation. And each of those has a different wavelength fixing mechanism, a different kind of position where it will appear on the track, a frequency, and what that damage mechanism is. So the first type is pinned corrugation. So the wavelength fixing mechanism is a resonance which is caused by the sleeper spacing, which is obviously usually a regular spacing in track, unless you're going through special track forms like switches and crossings where you might have different sleeper spacings. So essentially the rail is vibrating like a beam, which is fixed at both ends by the sleeper. And the frequency of vibration will depend on the sleeper spacing and also the mass per unit length of the rail, so the rail grade, and also the rail stiffness. So the wavelength of the damage will increase as the sleeper spacing increases and the rail stiffness decreases. So this type of corrugation occurs particularly in straight track or on the high rail of curves, and it has a typical frequency of between 400 and 1200 hertz. And the damage mechanism is wear. And what you tend to see with pinned resonance is that the wear damage tends to be more severe over the sleepers. So the second type of corrugation is rutting, which has been associated, or the wavelength fixing mechanism is associated with the resonance of the driven axles of the vehicles. And it's also linked to stick slip oscillations in the wheel rail interface as well, typically on the leading wheel of the low rail. And this leads to a short wavelength damage pattern, which is dependent on the vehicle speed, but is typically around 50 millimeters for a vehicle speed of 45 kilometers an hour. So this appears predominantly on the low rail of curves. The damage mechanism is wear, and the peaks of the wave are associated with the slip phase of the stick slip oscillation. So when the wheel is slipping, then that's where you get the damage. The third main type is P2 resonance, which is the wavelength fixing mechanism is associated with the suspension characteristics of the vehicle and how the resonant frequencies of that suspension and how it reacts with the track. Essentially, the mechanism is that the vehicle is essentially bouncing along the track, leading to the damage pattern. This type of resonance can occur in straight track or in high rail in curves. Wave C is lower than the pinned or the rutting corrugation and tends to be between 50 and 100 hertz. But similarly, the wear mechanism is, the damage mechanism is wear. There are other types of corrugation that have been identified where the damage mechanism is slightly different. So where you have plastic flow or plastic bending of the rail, and these have been identified in heavy haul and in light rail systems as well. So they're the types of corrugation that you might typically see. So how can we now mitigate against corrugation damage? So first and foremost, ideally, you should try and prevent corrugation by design. So designing it out of the track system, either by design of the track geometry, the track form, or also by design of the vehicles and their dynamic behavior and suspension characteristics. So multi-body simulation models can be, such as Vampire, can be used to predict wheel rail interface behavior of specific vehicle and track interactions, to try and design out the corrugation in the first place before the track is even built or the vehicle actually goes on the track. But obviously this is not always possible or feasible. It's an existing track and a new vehicle's going on it. So this is not always possible, but this obviously ideally you want to prevent it in the first place. So to control it, grinding or milling of the wheel or the rail profiles can be used to remove the corrugation damage and remove that wave pattern. But this is very much a treatment of the symptoms. It's not a prevention or a cure. So you're restoring the rail profile will also help to improve the wheel rail dynamics and improve steering to slow down that formation of corrugation. But the corrugation will return over time because the track geometry is fixed and the vehicle dynamics is fixed. Obviously, this is time consuming, and grinding or milling of the rail will significantly reduce the rail life, especially if the corrugation is very fast growing, because you're going to have to do that on a very frequent basis. And obviously is very costly in the long run. So you can also reduce the magnitude of the damage by using a harder grade of rail steel, which is more wear resistance. So the images here show 3 different rail grades. So from the left to the right, you have increasing hardness of the rail. So you have the R350 HT rail. So you can see, so these are all similar amount of traffic, similar amount of time in terms of corrugation growth. So the 350, you can quite clearly see the corrugations on the rail. Moving up to a 370 hardness rail, you can see that the amplitude of the corrugation has decreased slightly. It's still there, but it's much less. And then you're moving up to a 400 hardness grade rail, and the corrugation, although it's not easy to see on the screen, but there is a very, very slight waveform there, but it's much less. So that is an option for reducing corrugation damage. And then obviously the final option, which we're talking about today in terms of friction management, is to reduce the wear damage itself, but also to eliminate those stick-slip oscillations which will cause those particular types of corrugation, such as the rutting damage. So this is the table again of the types of corrugation, but now we've just added in the treatments that you can use. So there's 2 columns under the treatment. So the left-hand column is what's actually been successfully demonstrated as a solution or as a mitigating solution for corrugation. And the right-hand column is what is theoretically possible, but hasn't actually potentially been used or proven as being a successful mitigation. So for the pinned resonance corrugation, the harder rails have been proved to be successful in terms of slowing that corrugation growth, and also friction management in terms of reducing the wear. So theoretically, increasing the corrugation wavelength by changing the sleeper spacing should help with that as well. Rutting, friction management is primarily the mitigation that you can use. Hard rails will also help, but also changing the track geometry, changing the track form in terms of reducing the cant excess and potentially asymmetric profiling of the rails in the curve. So changing the wheel rail contact will also help with that. And then the P2 resonance, certainly harder rails and using a high resilience track form. So reducing or damping those vibrations of the suspension on the track will help to mitigate against that corrugation. Arguably, friction management will probably help with the P2, and in some cases, and in one of the case studies I'll talk about later, where we've had P2 resonance, friction management has been very successful as well. So in terms of the solutions itself, what can we use? So we've used this slide again in all of our webinars. So where we're talking about corrugation mitigation, we're talking about applying materials to the top of the rail only. So we can have a trackside solution, which will apply to the rail, and the consumable there is a friction modifier. We can have an onboard solid stick solution. So we're applying product to the wheel tread, which is then transferred to the rail, or we can have an onboard spray system, which is either applying product to the wheel tread or directly to the rail head. And here we're targeting a coefficient of friction between 0.3 and 0.4. So in terms of the hardware that we're using, for a trackside solution, we are using an electrical trackside top of rail unit. So only electrical units are used for top of rail. I'm not aware of any hydraulic or mechanical systems that are used for top of rail. This is primarily because an electrical unit will give you a precise amount of product applied, and therefore you're reducing the risk of any over application of product to the railhead. And this is particularly important if you're using an oil-based or a hybrid top of rail material that has an oil content. The sensitivity of application rates is very, very high for those types of top of rail material. So the applicator bars are fixed to the field side of the rail and apply product to the top of the rail. And typically the bars are placed in tangent track just prior to the start of the curve. And that's to maximize the wheel rail contact and the amount of material that you're going to pick up and carry down into the curve. For the onboard stick solution, you're using a tread stick applicator. So have the picture here. So this is stainless steel tube into which the sticks are loaded and held against the wheel using a constant force spring. So it's a very simple mechanical system. So you're applying product directly to the wheel tread, but then as the wheel rail interaction happens, you're transferring product to the rail as well. So you get the benefit of protecting the wheel as well as the rail as well. So simple system, no active control system is required, and the sticks regulate themselves in terms of the consumption. And then the final solution is a top of rail spray. So this provides the same benefit as a top of rail trackside unit, but gives the added benefit that you are, the equipment is on the vehicle. So you can apply in precise locations where the product is needed. So it's not restricted to one trackside location. It eliminates some of the operation and safety constraints related to top of rail trackside units, in that the maintenance happens within the depot. So you don't have to send people to track, so less boots on ballast. And also all of the maintenance and filling is carried out in the depot. So a much safer and much pleasanter environment than a trackside in the dead of winter when a gale is blowing. So in terms of the consumables, as I've said in previous webinars, there are several different types on the market, and these can be oil-based, oils in themselves, grease-based, hybrid, or water-based. So it should be noted that all of these products will reduce friction, and so will help to reduce the wear damage generated by corrugation. But not all will truly be effective against the prevention. So in terms of reducing the slip oscillations in the wheel rail interface. So here I'm only talking about Keltrack because that's the LB Foster product, obviously. So it comes in both trackside and onboard formulations. So it can be used in the electric units trackside or on the onboard top of rail sprays. The unique characteristic about Keltrack is that it's water-based. There are no oils at all in Keltrack, and it's a fairly unique formulation in that it's the only purely water-based friction modifier that's on the market at the moment. It doesn't affect traction or braking performance. So in terms of application rates, it's not as sensitive to over application as the oil or grease based. But the key thing in terms of corrugation is that it has positive friction characteristics. So we went through this last time in terms of how this works. So in the wheel rail interface, you have this third body layer that sits between the wheel and the rail. And in this, you have these hard, brittle wear particles and other materials. So the Keltrack actually sits between these particles. So Keltrack has a solid content of somewhere between 10 and 20%. So these very, very small solid particles sit in between the hard, brittle particles and actually cushion them and prevent them from breaking down, which cause this stick-slip oscillation cycle in the wheel rail interface. So instead of having this process where the particles roll together, squeeze together, break, and then the voids collapse, and then you get this negative friction, which you can see here. The Keltrack cushions those and you get a positive friction characteristic. So you never get into this stick-slip oscillation cycle. So for things like the rutting corrugation, where stick-slip is very much the wavelength fixing mechanism, that it's very, very effective at preventing that. So finally, just to round off, we've got a few case studies where we've used Keltrack. And the corrugation damage has been very, very effectively mitigated and the corrugation growth limited. So this one is a commuter rail system. So we have a curve radius of 227 meters, length of curve just under 500 meters. It's R260 grade rail, ballasted track with concrete sleepers. So you can see here is curve coming out of the station. We have, so the triangles denote where we applied the friction modifier, and the red circles where we actually measured the corrugation depth. So here we have the results. So on the left, we've got the reference profile or the reference period. So the rail was ground at the start of the reference phase, and then corrugation measurements were taken after 45 days. So at the end of the 45 days, the depth of the corrugation damage was 0.4 millimeters. So we then ground the rail again, and Keltrack was applied to the track from those application points. So after 280 days, corrugation measurements were taken again, and the amplitude, you can see here, the amplitude was only 0.005. So a very, very significant halt in the growth of the characteristic corrugation on that curve. And the similar pattern was shown on the second track as well, in terms of the growth of the corrugation. There was a slight difference between the two tracks because there's slight rail profile differences. The trains were going at different speeds and different accelerations through the curve. So not exactly the same behavior, but exactly the same pattern in terms of the halt of the growth. So this is a couple of pictures. So this is 30 days after grinding in the reference period, and this is the rail after 280 days without with FM being applied. So quite a significant difference. So an improvement factor of 27. Second one is from Japan. So this is on the Uedo line. So this is a curve radius of 101 meters and a length of 216 meters. So quite high traffic level, 210 trains a day. Wheel loads 30 kilonewtons empty, 42 kilonewtons full. It's 160% capacity. So Japan, a lot of people in that train. Originally they were using top of rail grease and onboard oil systems, but they found that these weren't effective, and so they ended that. And then they started to apply the Keltrack water-based friction modifier. So here we've got the table of results. So just looking down, you have the corrugation growth when they were using the top of rail grease and onboard oil. So you've got a growth rate of 0.055 millimeters per year. And then using Keltrack only, that growth rate has reduced to 0.01, even though you've still got a similar depth of corrugation damage. It slowed it right down to actually 0.01 millimeters per year. And in one of the locations, the bottom location, it's actually halted the corrugation growth altogether. Heathrow Airport Express. So this is a 330-meter curve, radius curve, coming out of Heathrow Airport. So the issues here were severe corrugation on the low rail. The wavelength was somewhere between 125 and 160 millimeters, and a typical depth of 0.8 millimeters. So this was actually attributed to P2 resonance. So this is related to the suspension characteristics of the vehicles. Secondary to that, they were experiencing a very, very high level of clip breakage. So average of 50 clips breaking per week. So they were having to go out, inspect the rail every week, and they were changing 50 clips each week. So as part of this, we did lateral force measurements to measure the lateral forces in the curve. We monitored the clip breakage frequency, and we also monitored the corrugation growth. We also did braking tests to ensure that there was no issue in terms of the vehicle braking. And we also tested the wheel rail isolation going over the insulated joints to make sure that any Keltrack bridging the insulated joints didn't affect the signalling or track detection at all. So you can see some of the results. So you can see the top right, the lateral forces were significantly reduced in the curving. The corrugation growth was actually reduced to a sixth of its original rate over time. And the clip breakage also went from that 50 clips breaking per week down to virtually zero. So again, very, very successful trial. The units are still there at Heathrow Express. I've spoken to them recently, and they have very, very little problems with corrugation there now. So in summary, we've recapped why we need to control friction, gone through some of the mechanisms of corrugation damage and initiation, looked at the friction management solutions and the consumables that we can use, and just gone through a few case studies. Finally, we've got still some webinars coming up. So our next webinar is on Wednesday, the 8th of January, and that is on low adhesion. And I will be joined by my colleague, Dr. Tom Butcher, who will be leading the main part of the webinar. Tom has been a member of my applications team for about 18 months now. And prior to that was at Sheffield University and has a PhD in low adhesion. So he is the expert to talk about low adhesion. Following that, we have webinars in February on energy consumption, March, derailment risk, and then finally in April, just a look at how you best get the validation and do trials with friction management. So how do you run a trial? How do you analyze the results? And how do you then best decide what friction management solution is the best for you? So all that remains is to say thank you very much for attending today. If I can, wish you a very happy Christmas season and a happy new year, and please join us in the new year. If you have any questions, please pop them in the chat, and I'd be happy to try and answer them for you.
So there was a comment from Stephen Wilson about a rail grinding train. I don't know if you want to have a look at that, Jackie, first, and then there's a question or two as well to look at.
Oh, yeah, sorry, I'm just taking a little bit of time to read it. Yeah, I mean, thanks for that comment, Stephen. It is very interesting. I mean, it is all about wheel rail interaction. So obviously, the track bed in itself, the ballast quality, the formation of the track bed itself will have an influence as well. Sounds like that was pin-pinned resonance potentially, because if your track bed's not as stable as it should be, then that vibration of the rail between the sleepers is likely to be higher as well. So yeah. Oh, next question. Yeah, Yungshi. Yes. I think the oil-based friction modifier was not effective because it was not effective against the stick slip oscillation. So where you have the Keltrack and the solid particles, and it prevents that stick slip oscillation, the grease or the oil-based ones won't, because they don't have that positive friction. They lower the friction, but they don't kind of combat the formation mechanism. And that's what we found in both in corrugation and also in squeal noise as well, where stick slip oscillations on the top of the rail are the mechanism for the formation of the squeal noise.
Stephen Lewis has also put a comment.
Oh, sorry.
In the Q&A as well.
Oh, where Stephen Lewis. Oh, it's not popped up. Can you read that out for me?
Of course. Not a question, but we have monitored an HP335 British Steel's premium rail test site over a 10-year period, and it has shown an increase in corrugation resistance of HB335 of between 3 and 4 times that of R260. This improves overall maintenance costs of the rail.
Yeah. Yep. I mean, I wanted to make sure that I didn't just talk about friction management today. You know, it's not a magic bullet. So there are other things that you can do. And certainly, as Stephen has quite correctly said, changing that rail grade, improving the strength of the rail can also be very, very effective. But combined with friction management, you couldn't get rid of it altogether. Thanks.
Unless anybody else has anything further, I think that may be it.
Yeah, thank you very much for tuning in. You'll get an email with the link to the recording if you really want to listen to it again. And have a lovely Christmas holiday, and hopefully I'll see you in the new year. Okay, bye.